at it and you'll be like, man, that looks terrible. But the actual process of deriving what we're doing, it won't be that bad. Okay. Okay, so we're starting on page 10. This is trigonometric integration or trigonometric integrals. This is the last thing that's going to be featured on the exam that you need to know. And so in this section, we're interested in looking at products of trigonometric functions and then taking the integral or finding the antiderivative. And for the most part, you don't really need, like, it may look like we'll be using integration by parts here, but for the most part, you can just use substitution to determine what the antiderivative of these functions are going to look like. And so we're going to go through a couple of examples to kind of develop an intuition about how you would tackle finding an antiderivative of this form. And then at the end, or at least on page 13 or page 12, like I'll give you a general algorithm for being able to solve like the integral of any like power of sine and cosine. Okay. And so first, let's just see, like, let's just use our intuition to determine what these integrals are going to be. And before I do anything, this is really the only trig identity you have to know in this class. This is one that should be familiar. If you do sine squared of x plus cosine squared of x, this is equal to 1. You should know this, or you kind of have to know this. Otherwise, you're not getting anywhere in this section. And then we'll do a variation of this involving tangent and secant later on. But if you know this formula, it's pretty much the only trig you have to remember, or trig formula you have to memorize in this class. You don't have to memorize like the double or half angle formulas or anything like that. Okay, so the first example we're looking at isn't even a product of sine and cosine. It's just sine cubed. And so we want to be able to evaluate what this integral is going to be. And at least on its face, it doesn't seem like we could really use substitution or integration by parts. But you can do something clever with this integral that we'll be doing frequently throughout today. So instead of writing this as sine cubed, you can write this as sine squared of x times sine of x dx. Then I guess I'll ask you, like, what benefit is there to writing sine cubed as sine squared times sine of x? Does anyone see it? Why would we do this? Oh yeah, you're raising your hand.
To change sine squared of x with cosine squared minus 1.
Yeah, exactly. So we want to use this formula. We have sine squared of x plus cosine squared of x is equal to 1. And so this tells us that we can rewrite, and it goes both ways. But for this example, this tells us sine squared of x is equal to 1 minus cosine squared of x. And so we can rewrite this integral in the following way. This is going to be the same thing as 1 minus cosine squared of x times sine of x dx. And then once we're at this step, what do we do next? What can we do? Yeah, now we can use substitution, right? We have a sine of x dx and we have a cosine that shows up. So if we let u be equal to cosine, this tells us then that du is going to be equal to minus sine of x dx. And so we can rewrite this integral in the following way. This is equal to minus 1 times the integral of 1 minus u squared multiplied by du. Right, the minus sign here just corresponds to the minus sign we had in front of the sine of x. And so now we have something that's straightforward to compute, right? We just need to use the power rule for integration here. So this is equal to minus 1 times the antiderivative of 1, which is u, and then minus the antiderivative of u squared, which is u cubed over 3. Then you add the c at the end and substitute back in for x. So this is going to be u is equal to cosine of x, so this is cosine of x minus the cubic power of cosine over 3 plus c. So this is how these problems go in general. They're, for the most part, going to be similar to the example that we just did. Okay, any questions about this example? Oh, the minus sign here came from, like, we let u be cosine of x, so if we take the derivative, we get a minus sine of x dx. And so we have, like, this is, we multiply both sides, we have minus du is equal to sine of x dx. So like the sine of x here becomes like a minus du. So I just brought the minus sign out in front of the integral. Yeah, another question. If you made it, I think it would be difficult. It might work out, but it would be difficult. Like if you let u be equal to 1 minus cosine squared of x, the du is then going to be 2 cosine of x multiplied by minus sine of x, because you have to do the chain rule. And then from here, like you have this extra, so this would be your u, but then you have like this extra like cosine of x. So I don't see how it would work out too well, or at least it would be more difficult. Okay, any other questions? Okay, and so this is going to highlight a trend that's going to hold true for the next example. So the idea here was we had an odd power of sine. And so what we did is we fractured off one of the signs to get a sine of x dx, and then we used the Pythagorean identity, i.e. this formula here, to then write everything else in terms of cosine, and then we let u be equal to cosine, so that way you take care of the sine of x dx. So the same logic is actually going to apply to the next problem. Even though the next problem looks a little bit more complicated, the idea or the process is the same. So for this next example, we want to evaluate the integral of sine to the 4th power of x times cosine to the 5th power of x. And so we look at the powers of these trig functions. We have an even power for sine, and we have an odd power for cosine. And so let's see what happens. Like, again, the last problem, we like for an odd power, we split off a power to make it so we ended up having an even power, and then we applied the Pythagorean identity. Let's see what happens if we apply the exact same logic to this example as well. And so what I'm going to do is I'm just going to rewrite this integral so that way, instead of cosine to the 5th power, we have a cosine to the 4th power. And so if we do this, we have sine to the 4th power of x multiplied by cosine to the 4th power of x multiplied by cosine of x dx. And so when we fracture off, like when we rewrite the 5th power of cosine as cosine to the 4th power times cosine of x, it leaves us with this cosine of x dx, which should give you a hint in terms of what you should be letting your u be equal to. I guess I don't know how I want to describe it. I'll just ask you, like based off of this, what should we let our u be equal to? Yeah. What we will do is like we're going to let our u be equal to sine of x, because then if we do du, we'll get a cosine of x dx. So this would be du. But we aren't completely done yet, right? Because we still have this 4th power of cosine that shows up. So if you perform this substitution now, you would end up getting the following. You would get, so sine to the 4th power is the same as u to the 4th power. We have cosine of x to the 4th power, and then we have du. And so we're still left with cosine to the 4th power of x. But we know a way in which we can translate even powers of cosine to even powers of sine, right? Like we use this formula again. And so another way of writing this, maybe I don't know if this makes things more confusing or not, but this is the same thing as u to the 4th power times cosine squared of x times cosine squared of x times du. And then we know from this Pythagorean identity that cosine squared is the same as 1 minus sine squared. And so this step, you don't have to write things out this way. I don't know if it would make it less confusing. So this is really the same thing as the integral of u to the 4th power times 1 minus sine squared of x squared, right? This is a 1 minus sine squared. This is a 1 minus sine squared. And so if you multiply them together, you get 1 minus sine squared squared. And then this is du. And then our u was equal to sine of x. So this 1 minus sine squared is really just 1 minus u squared. So this is equal to the integral from u to the 4th power of 1 minus u squared squared du. And so now it's just a matter of multiplying things out and then doing the power rule. So this is the same thing as the integral of u to the fourth power. We have a 1 minus 2u squared plus u to the fourth power du. This is the same thing as u to the fourth minus 2 times u to the sixth plus u to the eighth power du. By the power rule, this is then going to be u to the fifth power over 5 minus 2 over 7 times u to the seventh plus u to the 9 over 9 plus u. And so all that's left is just plugging in u is equal to sine of x, right? So this is going to be equal to sine to the fifth power of x over 5 minus this 2 over 7, sine of the seventh power of x plus sine to the ninth power of x over 9 plus c. Right, so this is the general strategy you're going to be applying. Like this holds true for both of the examples we looked at, even though the first example we weren't even multiplying by a cosine. So whatever your odd power is going to be, you're going to take one of those powers and then you're going to fracture it off and multiply it by dx. So we rewrote cosine to the fifth power as cosine to the fourth times cosine of x dx. And this is going to indicate what your u is going to be. If we have a cosine of x times dx, it makes sense we want u to be equal to sine of x. So when we take the derivative, it handles this part and makes it du. And then all that's left is translating the remaining trig function into something in terms of whatever your u is, right? So even though the problems look different, we really just followed the exact same steps in both instances. Okay, any questions about this example? Okay. Yeah, so these two examples are nice, and these are the two kinds of problems that you can expect to show up on the exam. The difficulty comes up or arises when you have an even power for both trig functions. And so if you have an even power for both of the trig functions, you want to be using something called like the reduction formula. So we have like these two reduction formulas that can be utilized whenever you have even powers of sine or cosine that show up inside of your integral. Really, it applies for like any power of sine and cosine, but you pretty much only use them when you have even powers for both. And so, the reason why this is ugly is just like, and look at these formulas; they're kind of disgusting. So you have like sine of x is equal to like minus 1 over n times sine to the n minus 1x times cosine of x plus like the power minus 1 over the power times the integral of sine to the n minus 2 of x. And then we have an analogous formula for cosine as well. So that's why I'm saying like these cases, these are nice because you can just follow your intuition and use u substitution and then this formula here. But if you have two even powers, you kind of have to use like these ugly looking formulas. Okay, and so we're going to derive actually this formula. And you'll see, actually, I don't know. I was going to say you'll see the derivation isn't that bad, but maybe you'll have the opposite opinion. Maybe it will look kind of ugly to you. Before going into this next example, we're actually going to derive this formula here, right? Because like this one, we have even powers of sine and cosine, so we kind of have to use this thing right here. Okay, so before going on to the next example, maybe on like the bottom half of the page or something, you can include this proof, or maybe on the back somewhere. Maybe on the back somewhere. I mean, you don't have to know how to do this. It's not going to show up on an exam or anything like that. But it is good to know in terms of like, it makes you more powerful mathematically, I guess. Okay, and so we're going to prove the following formula. We have the integral of the nth power of cosine of x, and we want to show that it ends up being equal to this thing right here. Okay, and so the first step here, I guess I'll ask you, does anyone see what the first step is going to be? Or like how we can rewrite this? Okay, go ahead.
You can rewrite it as the integral of cosine to the n minus 1x times cosine x dx.
Yeah, you can do that. That's a good idea. So we can rewrite this integral. So we have like the integral of cosine to the nth power of x dx. This is really equal to cosine to the n minus 1 power of x multiplied by cosine of x dx. And I will say, you don't want to be using the Pythagorean theorem here, or the Pythagorean identity like we did in the previous case. Like looking at the previous examples, we're like, we pulled this off and then we let u be equal to sine of x. That's not really going to get us anywhere because we don't know whether n minus 1 is even or odd. So we don't really know how that would play out. But this is like a good way of writing things out in terms of developing an intuition for what the next step is going to be, or like the technique we're going to use. Does anyone know like what technique we want to use here? Taking the integral of a product of two functions. Yeah, we want to use integration by parts here. And like, I guess like the meta strategy is like, we talked about integration by parts on Wednesday and we haven't used it yet. So like for this section to come up after integration by parts, like integration by parts should show up somewhere. But you should also think in terms of, we have like a product of two functions and we want to find the integral. So your first choice should be integration by parts. If it doesn't look like u substitution will work. And so we need to determine what our u is going to be and what our dv is going to be. They're both trig functions. So you need to think in terms of which function is it going to be easier to integrate, right? Like if we let dv be the n minus 1 power of cosine, you would have to integrate it to find v, but then we're at the same problem over again, right? And so we're going to let u, I'm going to make more space. We're going to let u be equal to cosine to the n minus 1 power of x. And we're going to let dv be cosine of x dx. Again, we don't want this to be dv because we don't know what the integral of this ends up looking like. That's kind of what we're trying to derive now. And so now we find du. So du is the derivative of u. So we have to use the chain rule here. So this is going to be n minus 1 multiplied by cosine to the n minus 2 power times x. And then you have to multiply by the derivative of cosine, which is minus sine of x. And then this is going to be, you have to have a dx at the end. And then our v is just the integral of cosine of x. So it's going to be sine of x. So what this tells us is we can rewrite the integral of cosine to the nth power of x in the following way. This is going to be equal to u times v. So this is going to be cosine to the n minus 1 power of x multiplied by sine of x. And you should note that this looks similar to what we want to ultimately prove. We're just missing this 1 over n in front of it. And then this is going to be minus the integral of v times du. And so let's look at what we have for our coefficients. So we have an n minus 1 in front. So we have an n minus 1. That's where this n minus 1 is going to show up. And then we also have a minus sine of x. So we have a minus sign, like this whole thing is being multiplied by minus 1. So we can bring that outside to make it so this is going to be a plus. And so then what's left? We have a sine of x multiplied by a sine of x. So we have a sine x squared, sine squared of x. And then we also have this cosine to the n minus 2 power. dx. Right, so I did a decent amount of cleaning. So I took the n minus 1 out, and then we had the minus 1. So like the minus became a plus. Okay, and so if you look at this formula, we have a sine of x squared here, right? Like we have a sine squared of x here, and we don't have a sine of x squared inside of the final answer that we have. So we should be like getting rid of the sine of x squared somehow. And one way of doing this is now by using the Pythagorean identity that we talked about in the beginning of class. So this is sine squared of x plus cosine of squared of x. So we can rewrite this integral as being equal to cosine to the n minus 1 power of x times sine of x plus n minus 1 times this integral. So instead of sine squared, we can have 1 minus cosine squared of x. Then this is multiplied to cosine to the n minus 2 power dx. And so what I'm going to do next I'm going to skip a couple of algebraic steps. So really what I'm going to be doing next is I'll distribute the 1 minus cosine squared of x to this cosine to the n minus 2 power. And then I'm just going to write it as two different integrals by linearity. So what I mean by this is the same thing as having cosine to the n minus 1 power of x times sine of x plus n minus 1 times the integral of cosine to the n minus 2 power of x dx. So that corresponds to this product here, like the 1 times cosine to the n minus 2. And then this is going to be minus what we have. So it's going to be minus n minus 1 times the integral of minus cosine squared of x times cosine to the n minus 2 power. So this is going to be minus n minus 1 times the integral of cosine to the nth power of x dx. Right, so I distributed the product here, and then I split it into two separate integrals. Okay. Oh, I should have left more space. Hold on. And so we're going to do a similar trick to what we did in class on Wednesday in the final example. So we have that this integral cosine to the nth power of x dx is equal to this thing here. Does anyone see what we do next if we want to solve for what this integral is going to end up being? Like, what's the next step? Does anyone see it? Yeah, so we have the same integral on both sides now, right? We have the integral of the nth power of cosine here and here. And so if we add this integral to the left-hand side, we would end up getting the following. So if we add this integral, so this is like we have a coefficient of n minus 1. So if we add it to this integral here, we're going to have a coefficient of n now. So we're going to have that this is going to be n multiplied by the integral of cosine, the nth power of cosine of x. And so this is going to be equal to cosine to the n minus 1 power of x times sine of x plus n minus 1 times the integral of cosine to the n minus 2 power of x dx. And maybe I should draw an arrow to indicate. And so all I did going from the previous step to this step is I added this quantity to both sides. So that's where this n comes from, right? We have like a 1 plus n minus 1, so you end up getting an n here. And so all that's left is we just have to divide by n now. And you see if we divide by n, we get the formula that we wanted to derive in the first place, right? So if we divide by n, we end up getting cosine. The integral of the nth power of cosine dx is 1 over n times cosine to the n minus 1 power of x sine of x plus n minus 1 over n times this integral of cosine to the n minus 2 power of x dx. And so the reason why this formula is helpful is you see that we're taking a power of n, like an integral of a power of n, and then we're reducing it into a problem of finding the integral of n minus 2, like a power of n minus 2. So we're reducing the power of cosine. So if you do this enough times, eventually this is just going to end up being equal to 1. Or it's going to be something that is easy to calculate. Like it's either going to be a cosine of x or it's just going to be a 1. And so we'll demonstrate this or why this formula is useful in the next example. Okay, any questions about the derivation of this equation? And I'll say, like on the exam and on the exam review, you do have to prove a reduction formula. It'll be like a lot easier than this one, like much easier than this one. But the idea is the same, like you'll have to rewrite the product so that way you use integration by parts. So there'll be a problem on the exam review similar to this. I think it's for a power of the natural log instead, but it's a lot easier to compute than this. Okay, and so where this shows up, now we can, I feel like we have to prove it to use it for the most part. So that's why I went through that proof. And so the reason why this is going to be useful is in the following example, we'll need to make use of it. And so for this example, we have the product of sine squared and cosine to the 4th power of x. And so to begin, what I'm going to do is like I'm going to write everything in terms of a power of cosine, right? Like cosine's the higher power here. So what I'm going to do is I'm going to take sine squared of x and I'm going to rewrite it as 1 minus cosine squared of x. And this is being multiplied to cosine to the 4th power of x dx. The reason why I'm doing this is after you multiply everything through, everything is going to be in terms of a power of cosine, and then you can apply this reduction formula. And so this is going to be the same thing as doing cosine, the integral of cosine to the 4th power of x minus cosine to the 6th power of x dx. And so now we can use these reduction formulas to determine these two, or we can determine the integral of these two powers. And so I guess I'll write it as an aside. Maybe I'll just do all of them right now. You can see if we have a cosine to the 6th power and we're doing the reduction formula, that means we'll also have to know what the integral of cosine to the 4th power is. And then eventually we'll have to determine what the integral of cosine squared is going to be. And so I'm just going to write them all out right here for convenience. So by the reduction formula, we have the following. So by this reduction formula, we have that the integral of cosine to the 6th power of x dx. So in this case, our n is equal to 6. So this is going to be equal to 1 over 6 times cosine to the 5th power. So n minus 1, that's 6 minus 1, so it's going to be 5 times x times sine of x. And then this is going to be plus n minus 1 over n, so 5 over 6, times the integral of cosine to the n minus 2 power. So again, n was equal to 6, so 6 minus 2 is 4. So this is going to be cosine to the 4th power of x dx. Okay. And so what this means is we can make the following substitution. So this is really the same thing as the integral. I'm actually going to split these integrals into two integrals. So this is really the integral of cosine to the 4th power of x dx minus this entire thing right here. So making the substitution for the integral of cosine of x, or cosine to the 6th power of x dx. This is going to be minus 1 over 6 cosine to the 5th power of x sine of x, and then plus 5 over 6 times the integral of cosine to the 4th power of x dx. I kind of ran out of space a little bit. But all I did was just substitute in this formula for the integral of the 6th power of cosine. And so we can do a little simplification here, actually, right? Because we have the integral of cosine to the 4th power, and then we're subtracting from it 5 over 6 times the integral of cosine to the 4th power. And so this is really going to be equal to 1 over 6 times the integral of cosine to the 4th power of x dx minus this quantity here. So this is going to be minus 1 over 6 times cosine to the 5th power of x multiplied by sine of x. And it's maybe it like looks a little bit confusing, but this quantity here is outside of the integral. We don't have to do anything with this. All that's left is just finding the integral of the 4th power of cosine now. Before I continue, are there any questions so far about what we've been doing? Yeah, question. Oh, yeah. So where this comes from is we already had the integral of cosine to the 4th power dx. And we also have a 5 over 6 times the integral of cosine to the 4th power of x inside of this quantity here. So we're just taking this integral and then subtracting by 5 over 6. So if this is like a really like saying we have a 6 over 6 times this integral, and then we're subtracting the 5 over 6. So that leaves us with a 1 over 6 integral here. Right, like all we're doing is combining like terms. If you treat this like a variable u, we're really saying this is like u minus 5 over 6 times u. Any other questions before I continue? Okay, and so all that's left is just applying the reduction formula twice. We need to apply the reduction formula to cosine to the fourth power. That would look like the following. So the integral of cosine to the fourth power of x dx. This will be equal to 1/4 times cosine cubed x times sine of x plus 3/4 times the integral of cosine squared of x dx. I'm going to continue. I'm not going to have enough space to write this out. So this is really the same thing as 1/6. So you see, this looks like it's kind of a disaster. Like there's so much we have to write out here. So this is 1/4 cosine cubed of x sine of x plus this 3/4 times the integral of cosine of x or cosine squared of x dx. And then we also have to remember to subtract by, it's like 1/6 times cosine to the fifth power of x sine of x. What's worse, there's still one more line I have to do at the end. And so like the final step is we just need to determine what the integral of cosine squared is. And you can again apply the reduction formula. And so the final reduction formula, we have that the integral, and there's other techniques you can use here as well. You can use like more traditional trig identities, but I'm just going to do this. So by the reduction formula again, this is 1/2 of cosine of x sine of x plus 1/2 times the integral. So we have cosine of 0 or cosine to the 0th power. So I'll just give us a dx. And so instead of writing the integral of, maybe I'll keep it like this for now, actually. I forget I was going to say anything. Okay, and so we're finally done. We just have to write out this final line by substituting in like this, what we have here, into this cosine. So this is 1/6 times 1/4. I'm just going to write it out. I'm not going to say it. It's just a mess. So this is 3/4 and 1/2 cosine of x sine of x. This 1/2 integral of dx, this is just 1/2 of x, right? Like if you do the antiderivative of 1, you just get x. So this is 1/2 of x. And then this is minus 1/6 cosine to the fifth power of x sine of x plus c. Okay, something like that. I don't know if did I substitute? Maybe I think everything should be good. I think everything should be good here. You can like multiply things out and simplify things, but I don't see the point of doing that. I kind of want to just move on. But this is right. This is why we don't like when we have like when they're both even powers, you kind of get these disasters that happen. And if you do have the two even powers, like you want to refer to these reduction formulas. On the exam, I don't really plan on you having to use these reduction formulas. But it might show up on homeworks, group works, quizzes. Like you should have an understanding about how you would apply these reduction formulas, right? Or I should say, like, I'm not going to ask you to do like the reduction formulas for like these trig functions specifically. I'll do something that's a lot easier. Okay, any questions about this example? Okay, so I'll move on to something nicer. Before I move on, just kind of want to summarize everything that we've done so far today. So this kind of gives you the thought process or the flow chart whenever you want to find the integral of a product of sine and cosine. And so the two easier cases are when we have odd powers. So if we have that the power of m or the power of sine is odd, this means you fracture off one of the signs and you let u be equal to cosine of x. So this was the first example we went through today. Similarly, if we have the power of cosine is odd, you split off a power of cosine and you let u be sine of x, and then you do u substitution after doing like the Pythagorean identity, and that's nice. And then if m and n are both even, you just use the reduction formulas. This is the bad case. Okay, and so we can generalize these ideas. So far, we've only been looking at products of sine and cosine. But you can also apply the same logic to integrals that have secant and tangent inside of them as well. So we'll go through two more examples and then we'll call it a day. Let's see. Yeah, and so, I mean, the main idea, again, that we're going to be utilizing, or the main trig identity we're going to be utilizing in these situations is the following. So we have cosine squared plus sine squared of x we know this is equal to 1. If we want to transform this equation so that way it involves secant and tangent, what we would do is we'll divide both sides by cosine squared. So if you divide everything by cosine squared of x, I kind of wrote that out in a weird way, but this is 1 plus tangent squared of x is equal to secant squared of x, right? So this is the relation we have between tangent and secant that we want to make use of throughout these next couple of examples. And so this is going to play by a different rule book than what we did for sine and cosine. It's like sine and cosine, whenever we had an odd power, it made sense to fracture that power and then let u be something whose derivative is equal to that. But like the derivative of tangent is secant squared, and the derivative of secant is secant tangent. So like the derivatives are a little bit different, so you have to play by kind of like a different rule book here. And so what ends up working for this example, so first we'll just follow our intuition and then we'll formalize it later on. So for this example, we have an odd power of tangent. And an odd power of secant, derivative of secant, in terms of like what do we want our u to end up being equal to. And so what we can do here is we can do the following. So you can see if we reduced the power of tangent and the power of secant by 1, we would have a tangent squared and then a secant to the 4th power. And if we have a tangent squared, we can use this formula to translate it in terms of secant. And so let's see what happens if we reduce or factor out a tangent and a secant. So if we do that, we get tangent squared of x times secant to the 4th power of x. And then you multiply by secant of x times tangent of x dx. Let me put a box around this. Okay. And so if we have the following integral, like what do we want our u to be equal to in this case? Yeah, we want it to be secant. Like the derivative of secant is equal to secant of x tangent of x. And so let's just see what happens if we let u be equal to secant of x. If u is secant of x, du is secant of x times tangent of x dx. And so this integral transforms in the following way. So this is going to be tangent squared of x times u to the 4th power. And then secant of x, tangent of x just becomes du. So all that remains is we just need to rewrite this tangent squared of x in terms of u. And we can do that by utilizing this formula here. And so tangent squared of x is really just equal to secant squared of x minus 1. So this is going to be equal to the integral of secant squared of x minus 1 times u to the 4th power du. Our u was equal to secant. So this is the same thing as the integral of u squared minus 1 times u to the 4th power du. And if you multiply things out, this is u to the 6th power minus u to the 4th power du. So all that's left is using the power rule. So this will be u to the 7th over 7 minus u to the 5th over 5th plus c, or 5 plus c. And then you plug in for secant. So this is secant to the 7th power of x over 7 minus secant to the 5th power of x over 5 plus c. So in taking away or factoring out the secant tangent, we made it so like the power of tangent ended up being even, which made it so we can eventually translate everything in terms of secant. And we also have it so if we let u be secant, the derivative ends up being secant tangent. So everything translates really nicely. Have any questions about this example? And then on the last page, there's like, I do another one of these like algorithms that shows you exactly like when you want to be using what for your u. Be something you put on your note card or something like that. And the last example, I have to go a little bit faster here. But for the last example, the idea is we have an even power of secant, and we know the derivative of tangent is secant squared. So it makes sense to write out the integral in the following way. So I'm gonna go a little bit fast here. Oh, and I'm doing the last example. The next example is kind of easy. You let u be equal to tangent. You get secant squared of x dx as your du. It's more basic. So this one's a little bit more interesting. So we're going to rewrite it in the following way. So this is times secant squared of x times secant squared of x dx. So we want to do this whenever we have an even power of secant, because now if we let u be tangent, the derivative will be secant squared. And we can write secant squared in terms of tangent via this reduction formula. And so this is, if we let u, actually let's write it like this. So this is the integral of tangent to the 6th power of x. Secant squared, this is the same thing by the Pythagorean identity. It's having 1 plus tangent squared. This is times 1 plus tangent squared of x. And we're multiplying by secant squared of x dx. And so we can let u be equal to tangent of x. So now du is going to be equal to secant squared of x dx. And we can rewrite this in the following way. So anything involving a tangent is immediately transformed into u. So this is really the integral of u to the 6th power times 1 of x dx just becomes du. So you multiply things out, and then you can use the power rule to determine what the integral is going to be. So this is going to be u to the 7th over 7 plus u to the 9th over 9 plus c. And so translating back in terms of x, this is tangent to the 7th power over 7 plus tangent to the 9th power over 9 plus c. And again, things play out the exact same way whenever you have an even power of secant. If you have an even power of secant, if you let u be tangent, things just work out. Any questions about this example? Yeah, so at the bottom of the page, I outlined the general strategies. So if you have that the power of tangent is odd, and we have the power of secant is greater than or equal to 1, you let u be secant. And then if you have an even power for secant, you can always just use u is equal to tangent. And I'm not going to cover the case when m is even and n is odd. You have to do the reduction formulas again, but it's not going to show up in this class. What's that? I can't.
I didn't take the first.
Oh, yeah. I mean, this is from my other class, but it's online. Like you can find them on like modules, and you can do it and turn it in by Tuesday. Yeah. So like this is the last content that the exam will cover. Yep.
Where did secant square at the end go? So for 10 to the 6, 1 plus tan squared times secant squared. What did you do with the secant squared at the end?
Yeah, so that was the du right here. So we let u be tangent of x. So if you take the derivative, you get secant squared of x dx. And so like the secant squared of x dx just becomes our du at the end here. And then everything else is in terms of tangent. So we can express it in terms of u. Does that make sense?
Yes.
Did you have a stapler? I didn't see
Oh, I
that.
actually do have a stapler.
I didn't stapler these group words.
Thank you.
For the even powers of like secant and cosine, like that means sine and cosine. Can we not just use like double angle formula with the trig identity and like solve it that way? Because I
You
learned
could.
like that, and then the book also has a way to like solve it that way.
I think there is a way. Like, of course, if you just have like sine squared or cosine squared or something like that, you can definitely do it that way. I think for like the higher powers of like if you have like cosine to the 10th power or like 8th power or something like that, the reduction formula is like it's more powerful. I think it's like easier to use. I haven't really worked through an example in terms of like doing like the integral of cosine to the 10th in terms of like the angle formula.
I haven't done it yet, but I think I might try out to see which one is better because I personally feel like the double angle formula, the trig identity is like a lot easier than this.
Yeah, it could be. I think in smaller powers it is, but for higher powers it's more difficult. So,
but like, can we use that formula if we have like a smaller power? Then
oh yeah, certainly.
Instead of
Like
doing
whatever,
all this.
yeah, whatever you
Okay.
want to use is available to you.
Alright.